Here's number 19, looking at some adding intervals properties of integration. So this is the question that the student was asked to do, and there's the student's attempt, so you can pause the video and have a go. Alright, so just going to look at a little bit of theory before we look at the actual problem. So this is one of the properties of integration. It's called the adding intervals property, which means if I want to integrate between 2 points, I can actually split it into 2 journeys. So as an example, this could be A and this could be C. So if I want to integrate between 0 and 2 of whatever this function is, I could also achieve that by putting a B in between. So here's A, here's B, here's C. It'll be this definite integral, the area under the curve. I could do it in 2 parts. I could do from 0 to 1, and then from 1 to 2. I get the same result. Here's the first area, and here's the second area. So we're going to use that property without any sort of loss of generality in that problem that you're having a go at. So you've done a great job having a look at the problem, identifying how you're adding 2 functions here and splitting it up into 2 integrals. Okay, that's a great start. Our next goal is to just change the order of these so that these 2 are together, so we can see what we're doing. So now that we have them in order, addition is commutative, we can change its order. We can see that we have that situation, the adding of intervals now, so we can combine those 2 yellow ones to integrate just between 2 and 5. So there we are, and from your problem, you know that this is 12, and you know that this is an integral that you can do by yourself. So just quickly in terms of the other 2 problems you had as well, so there's a property that also tells us that you can take a number, just a constant that's inside an integral, outside the front of the integral. So it needs to be a constant, obviously. So for example, over here, I've got this function and there's an area underneath it between 0 and 2. If I then multiply it by 3, I'll have 3 times the area. Okay, if I multiplied it by x, it'd become a completely different function, so only numbers we're allowed to pull out the front of the integral. So in terms of this problem, you would be just making it 3 times the integral from 2 to 5 of that function with respect to x. And you know that it'll just be 3 times 12 because you're given what that area under that original function was. And finally, for the first problem, we're using the reversal of bounds theory. So if I'm doing a normal integral under a function, I'm breaking it up really into those little rectangles. And when I'm going from A to B, like going from 0 to 2, the width of these intervals is positive because that little change I'm making each time is positive 0.2 because I'm going in that direction. If I change it to the other way, so this is integral of 0 to 2 standard. If it said I have the integral of 2 to 0 of that function, I'm starting at 2 and I'm breaking it into rectangles going this way. So my change in x is really negative 0.2 all the time. So all these rectangles traveling in the opposite direction have negative area, which is why there's a negative sign here, that these 2 differ by a factor of negative 1. They're negatives of each other. So the problem that you're asked to do of integrating from 5 to 2, you can think, hey, that's just the same as integrating from 2 to 5, but a negative of that, so end up with negative 12. Okay, so hopefully that's maybe cleared up some of those properties of integrations for you. If you have any other questions, feel free to ask on the FB page. Good luck.